Hello everyone, my name is Andrea. I'm a second year PhD student from the University of Bologna, and I'm mainly interested in dark matter phenomenology and more broadly astroparticle physics, and specifically in the context of dark sectors. And today I want to tell you a little bit about some work I've been doing over the past year um, on phenomenological signatures of dark matter around blazars. And I want to ask this question: did IceCube detect dark matter around blazars? So I know this is a very uh, provocative question. I realize that, but I hope by the end of the talk you think it's maybe an interesting prospect and something worth looking into. This is the structure of the talk. So I'll tell you a little bit about blazars, what they are and how they work. I'm not an expert, so I'll just keep, some info that we need for the context of this talk. And then maybe depending on your context, depending on your background, you don't really know that much about these objects, or maybe you know way more than I do. Then I'll tell you a little bit about dark matter, which I'm sure everyone is familiar with. And then I'll tell you about two phenomenological signatures of this interaction between these two components, which are blazar boosted dark matter and neutrinos from blazars. So let me start by talking about blazars. What are blazars? Well, they are a subclass of active galactic nuclei, or AGNs. And AGNs are the central region of some galaxies that are extremely bright and extremely powerful and across the entire electromagnetic spectrum, so much so that they often outshine their host galaxy. And the only engine that can power something like this is an accreting supermassive black hole. So you can see here in this little picture, we have the supermassive black hole in the center. It's a accretion disk, a very complex environment that we're not gonna be interested in, but it's very interesting in its own right. And then we have in some AGNs a pair of back-to-back ultra-relativistic jets. That is what we're going to be interested in. Now you can see that this object is extremely anisotropic. So depending on where you are with respect to the orientation of the system, you will see different phenomenology. Specifically, if the jet is pointed towards us or closely aligned to our line of sight, we call these objects blazars. So blazars that we have the jet aligned to our line of sight. Here we have some very cool pictures of some AGNs. These are not blazars because the jet is not pointed our way, but if you were here, you would call that object a blazar. And now we want to understand how these objects work. And to do so, we need to look at their electromagnetic emissions. So this is a spectrum of one of these blazars. It's just the flux times E squared for convenience. And down here you have radio waves and microwave, infrared optical UV. This peak shifts a little bit in these frequencies depending on the object. We have a dip down here in the X-rays, and then a second peak up here in the gamma rays. And if we want to say that we understand how these objects work, we need to have a model that describes this electromagnetic emission. So one such model, which is a very popular way to describe these objects, is the so-called one-zone leptodronic model. And in this model, you have that the supermassive black hole ejects a blob of stuff. And this blob moves with a very high relativistic factor towards us, so in our direction. And the blob is filled with a lot of high energy protons and electrons. And besides this, there's a lot of ambient photons from the accretion disk, from the environment, and from the radiative processes in the jet itself, so in the blob itself. So how does this describe the double bump spectrum? Well, the first bump at low energies is due to electron synchrotron radiation. So these blobs are very magnetized, and the electrons just radiate in this electromagnetic field, in this magnetic field. They do synchrotron radiation, and this explains the first peak. The second peak is due to electron inverse Compton onto either ambient photons or on the synchrotron photons themselves, which is called synchrotron self-Compton. Then we also have protons, as we said. So what do they do? Well, they can do proton synchrotron. They can do Bethe-Eitler cascades when they interact with photons, or they can do photomeson production. So they interact with the photon and create a pion. And depending if the pion is charged or neutral, if it's neutral, it will decay into gamma rays. They will pair produce and do a whole electromagnetic shower. If it's a charged pion, it will decay, create muons, and they themselves decay, and they will do another separate electromagnetic shower, and they create neutrinos. this is this bump up here. So we expect these objects to be neutrino emitters, and keep this in mind. Keep this in mind because it's going to be important later. So this is all the context that you need for the purpose of this talk. Second ingredient is dark matter. So I'm sure everyone is familiar with this. Why do we need dark matter? Well, there's evidence, overwhelming evidence across all scales from, sorry, let me just move my face, from galaxy rotation curves to galaxy clusters to the large scale structure to the CMB to basically everything. But despite this, we know very little about dark matter. So we know that it interacts gravitationally. We know that it's cold at the time of structure formation, that it's collisionless, and that it is somewhere in this mass range, in this 80 orders of magnitude mass range. And across this range, there's a lot of interesting and well-motivated candidates that can fit the bill of being dark matter. I cannot cover this entire range, so I'm going to focus on the light dark matter range. So fermion dark matter, sub-GeV in mass. Okay, so why this mass range? Why is it interesting? Why do we think there might be something there? Well, the most well-motivated fermion dark matter candidate is the WIMP, but we have not had any luck finding yet. At colliders experiments, at direct detection experiments, in direct detection, we still have not found it, even though there are some interesting hints. So since we expected to find it, we've been expecting to find it for a while, and we're not finding it yet. This opens the possibility to have consider other candidates, and specifically, I'm going to focus on sub-GeV in sub-GeV range, where we have dark sectors. So dark sectors are one particle or many particles that are standard model singlets and only interact with the standard model through proton interactions. And this proton interaction allows to have naturally small couplings and can unlock the sub-GeV mass range without, it's okay to not have seen such a light particle just because the interaction is so small. Okay, another interesting hint for physics at the GeV scale or sub-GeV scale is the PTA signal. It was first detected by Nanograv and then by all the other PTA collaborations. So of the stochastic gravitational wave background. So the astrophysical explanation is a lot of merging supermassive black holes. Another possibility is that it's a signal of a first order phase transition in the early universe from a sub-GeV dark sector. So, it can explain that signal, and it's a very interesting possibility. So it points towards this mass scale. Another interesting observation is the 511 kV line from the galactic center, which seems hard to explain only through astrophysics. Of course, it's possible it's just astrophysics. Obviously it would be super interesting if it's an astrophysical signal, but since it's hard to explain, that leaves open the possibility that maybe it's a signal of annihilating dark matter. So this again points to maybe new physics at the GeV scale or below the GeV scale. Okay, so if you buy this, another ingredient we need is a spike. So we expect that around these supermassive black holes, the density of dark matter should have a spike. And the reason is that as the supermassive black hole grows and accretes, it adiabatically contracts the surrounding halo. So it grows a little bit and contracts the halo around it, grows a little bit more, contracts the halo. And this turns an initial NFW profile into a more peaked, spiked version, as you can see in the plot. So from the green line, it can turn into the red or blue or black line, depending on how you expect this process to happen. And this, in the most promising scenario, can give us, for the line of sight integral, so the column density of dark matter, which is what we're going to be interested in, 8 or 9 orders of magnitude increase with respect to the NFW exploitation, which is amazing for phenomenology. If you want to see a signal, 9 orders of magnitude is an amazing enhancement for free. Of course, this is just the ideal case. So in the ideal case, you get this enhancement, but we don't live in an ideal universe. So you can have galaxy mergers, you can have dark matter annihilation, you can have thermalization with the surrounding stars that can reduce the spike, which you still expect a spike to be there generically, but maybe not 9 orders of magnitude enhancement. now, as I mentioned, with all these possible effects, it's very hard to actually make a prediction on what this spike should be. So we just chose two benchmark values of 3,000 enhancement with respect to NFW and a more aggressive million enhancement of NFW. These seem like reasonable benchmarks if you don't know actually how the process happens, but we can discuss whether they're actually reasonable or not. But yeah, so now we have this spike of dark matter. We have the model for the jet of the blazar. Now we can do some phenomenology, and we will look at two signals. So you have protons in the jet bumping into the dark matter, and then we look at what comes out. Either you can look at the dark matter coming out of this interaction, which is blazar boosted dark matter, or you can look at what happens to the proton. So if the collision is hard enough, you will be in the deep energy scattering regime. The proton will break apart, shower, do a bunch of things, and then at the end you get a lot of neutrinos. So you will look at neutrinos from blazar as a signature of this interaction. So first, blazar boosted dark matter. Why will we boost the dark matter? Well, the reason is that if you go below a GeV in mass, below a few GeV, direct detection experiments lose sensitivity because the halo component of dark matter does not have enough kinetic energy to leave a detectable recoil in direct detection experiments. So you can do two things to overcome this. One is to lower your detector threshold, and there's a lot of experimental effort to devise new techniques and new types of experiments to lower this threshold and look at directly at the sub-GeV mass range. A lot of interesting ideas and possibilities. Another way you can do it is to increase the energy of the dark matter, so you can still leave a detectable signature even if the mass is lower. And one way to do so is by boosting it via its interaction with cosmic rays. So cosmic rays going around the galaxy, if they interact with dark matter at all, some of them will bump into dark matter, give it a boost, and now you have a subpopulation of dark matter which is very energetic due to this interaction, and you can look for that. And this unlocks direct detection even for sub-GeV masses, and gives some very interesting prospects. If you want to do better than galactic cosmic rays, you need to look somewhere where there are more cosmic rays, more dark matter, and higher energies. And as we described for the past 10 minutes, ideal place to look for this is blazars. So we will look at blazar boosted dark matter. Now we have to commit to a specific model. So our model is that we add a new fermion, that is dark matter, and a massive vector mediator. And we then can compute the flux using this integral here. And here in red is the information from the spike. In blue is the model of the jet, and in green is the particle physics model. You put all this info in, you compute the fluxes, and you get these fluxes. Now, in dashed is what happens if you don't commit to any specific model, and in blue, in a solid, is what happens if you choose our specific model. But in general, committing to a specific model rather than considering a constant cross section gives a large increase. And you can see here that there are the dark matter goes to TeV, tens of TeV energies, so you can do direct detection at super chemicande, possibly at IceCube, at large neutrino experiments. Now, this all sounds good, but if you add a new mediator, there are bounds on the mediator itself from meson decays. Even stronger, we consider UV completion by gauging baryon number, and this induces a new Z gamma V vertex. So the strongest bound is from Z to gamma invisible decays at lab, which is UV model dependent, so it can be avoided in a different UV completion. And this is what we get. So if we take into account this new bound from UV completion, we can manage to cut out a new smallish, very small, thin sliver of parameter space, but that can increase at future experiments like Dune. And this is all very interesting and cool. What happens if we instead look at the neutrinos? So in 2017, IceCube detected a neutrino from this particular blazar, and it's the first time that they managed to associate one of the neutrinos to a specific physical source. Since then, they've looked back through the data and found other neutrinos from the same source and other neutrinos from other blazars. So this motivates the fact that blazars are high energy neutrino sources. And as we said, we expect this to be the case. But in general, these models underpredict the neutrino flux with respect to this observation of neutrinos. And this is a kind of a puzzle in AGN physics of how to have such large fluxes of neutrinos. There are alternative models. maybe a cloud from the broad line region passed in front of the jet, and this gave a lot of hadronic interactions and a lot of neutrinos. You can have multi-zone models. So with more complex models, you can maybe explain this neutrino, but there's no consensus yet. So what happens if you do proton dark matter collisions? Well, you can compute the flux using this whole thing, where we use Malgraph and Pythia to do the particle physics side of this interaction. And what happens? Well, here's the plot from earlier. And if we put in our numbers, we get this. This is the flux that we predict. And of course, I tuned it so that it fits perfectly, but there's a large part of unrestricted parameter space where I can do it. In fact, everywhere within this blue band, depending on your spike profile, you can explain the neutrino this way. So very interesting. You can, this for unexplored parameter space, you have more neutrinos in the standard model, and you can explain those neutrinos naturally, let's say. Is this a fluke? Is this just this one particular blazar? Well, we took a lot of blazars where we have leptodonic fits. We did the same thing for all these blazars, and you can find here this cumulative flux from all these blazars. And I tune it so it passes through the diffuse flux of neutrinos observed by IceCube. But again, I can do it for a large part of parameter space. So everywhere in this green band, I can do it, depending on the spike profile. And I don't want to claim that this is the source for the diffuse neutrino flux, also because it's not clear whether that's actually correlated to the blazars chi-map. There are hints that maybe it is above 100 TeV, which is what you would expect from this mechanism, but I don't want to make that claim. Still work to be done, but it's interesting that you can get a very large flux this way, summing over all blazars. So key takeaways: you can probe very small cross sections using boosted dark matter. You can, if you have even smaller cross sections, you get more neutrinos this way than through standard model processes. You can explain neutrino emissions from blazars this way for unrestricted parameter space. So this brings again the question from the title: did IceCube detect dark matter on blazars? I don't know, but I think it's an interesting thing, and I hope you think it's an interesting possibility. And this is some more work to be done. So in this process, you only also produce gamma rays. Does this mess up the fit that we're using in the first place? What happens if you look at other types of AGNs, which are also expected to be neutrino producers? Is the spike reasonable? Could this be a contribution to the diffuse neutrino background? And then, of course, there are very large uncertainties. So can we quantify them somehow, the uncertainties from the modeling of the astrophysical environment? And with that, I thank you. And yeah, thanks.